Dr. John Donohue is the Senior Manager of Scientific Outreach at the Institute of Quantum Computing, IQC, a research institute at the University of Waterloo. John is responsible for making quantum science accessible for everyone, including through educational programs like the undergraduate studies in experimental quantum information processing, USCIP. John earned his PhD from the University of Waterloo in 2016 for work in quantum optics. We really want this talk to be kind of your first step to learning more about quantum computing. So we hope you enjoy.
Perfect. Thank you so much, Vivek. All right. Hi, everyone. How's it going? Good? All right. Awesome. So my name's John, and thank you so much for having me, coming, as mentioned, from the Institute for Quantum Computing at the University of Waterloo. Thank you to Vivek, thank you to Moji, thank you to everyone who put together this conference. I'm really excited to be here. Thank you to you all for joining as well. So for the next little bit, I'd like to talk a little bit about qubits. So just as a quick heads up who this is for, I did get a chance to take a peek at a couple of the posters. I'm looking forward to getting a chance to dive into some of them a bit more deeply. But I'm hoping that there's a couple of you who just saw that this conference was happening, have no idea what any of this quantum stuff is. People are throwing around these terms and you're like, what the heck are they talking about? So I'm hoping that there's a few of you peppered out in here. Okay, I see a couple hands. Okay, this is for you. I'm going to be looking at you the whole time, okay? You specifically. If you don't know what a qubit is, you don't know what any of these things are, this is for you. Please feel free to interrupt me at any time with questions. If I don't get through everything, that's not the end of the world. So before we talk about qubits, a qubit, we know that stands for quantum bit. If we want to know what a qubit is, we got to know what a bit is. So does anyone, what is a bit? Yeah, at the back? Smallest unit of data, yeah? Okay, oh, sorry? Okay, the smallest unit of data. Any other definitions? That's not wrong. There's a lot of valid definitions here, yeah? Something that has two categories of information, usually recognized as true, false, or 0, 1. Anything else? Yeah? Funny joke, yeah, okay, a bit, yeah. Okay, yeah, it's good to do bits. So I'm a physicist by background. So when I hear what a bit is, yeah, abstractly, absolutely. It's the smallest unit of information. It's something that can be true, false, or 0, 1. But the important thing is that it's something. If I want to have a bit of information, I need to encode it in something physical. So a bit of information can be encoded into any physical object that has two mutually exclusive states. So Stephanie mentioned briefly like mutually distinguishable states. Mutually exclusive states means the same thing. Two states are mutually exclusive if they are distinguishable and impossible to confuse to a perfect measurement device. And they cannot both occur at the same time. So bits of information might be encoded in the electronic state of a transistor, for example. That's what we use in our phones and everything like that. But abstractly, it could be anything. It could be whether or not a coin is heads or tails. I can encode a 0 or a 1, say 0 corresponds to tails, 1 corresponds to heads. It could be whether a light is on or off, whether a light switch is up or down. Maybe I have a light that can be either red or blue, or maybe baroquely I can have a cat that is alive or dead. Technically, I can use that as a bit. It's a very classical bit, but the cat being alive or dead, if I open the box and find the cat alive, that's 0. If I open the box and find the cat dead, that's 1. I would not recommend doing that experiment, but nonetheless, I can encode information in a bunch of cats in that way. So I can have these kinds of things come up in quantum mechanics as well. So one of the ways, if you've taken like a second or third year quantum mechanics course, you've probably seen the Stern-Gerlach experiment. If you haven't seen the Stern-Gerlach experiment, don't worry about it. The lesson from it is that if I have a single electron, it can have one of two possible values of angular momentum. A form of spin angular momentum. It's not actually spinning, but let's pretend it is for now. And it can be spinning this way around, or this way around. Only those two options. We call those spin up and spin down. So this is a system that is quantum mechanical in nature that has two mutually exclusive states. Thus, it's a system that I can encode one bit of information into. If it is spin up, that's a 0. If it is spin down, that's a 1. There are other systems that I can find two mutually exclusive states for that also obey the laws of quantum mechanics. We talked a little bit already about photons. I could have a photon, and I could say if I have my individual unit of light, my one photon, it is over here. I'm going to call that a 0. If I find my photon over here, I'm going to call that a 1. Or I could look at the polarization of light. You all received a little polarizer when you joined up here. So light is an electromagnetic wave. It has an electric field with it. That could be oscillating side to side like this. We call that horizontal. Or up and down like this. We call that vertical. I can encode a bit of information by saying if it is horizontal, that's my 0. If it's vertical, that's my 1. And even when I have a single photon of light, it still carries an electromagnetic field that has a defined direction. Okay, so a quantum bit or a qubit may be encoded into a system that obeys the rules of quantum mechanics that has at least 2 mutually exclusive states, 2 well-controlled mutually exclusive states. Okay, now usually what we'll see is we'll start writing these down as vectors. So let's consider electron spin for right now. We'll make this a bit more concrete in a bit, but we usually represent our qubit states as pairs of orthogonal vectors. So for example, I would say my spin up state would be this 1, 0 vector. My spin down qubit would be this 0, 1 vector. Okay, so unit vectors, think about like the x and the y vector, standard linear algebra. There's a few rules they have to obey, which in a half hour we can't get through all the rules, but here's kind of why some of these things matter. Why do they have to be orthogonal? Well, we want to make sure that we're representing the fact that these vectors, these bit states, are mutually exclusive. They're impossible to confuse. I can design something that distinguishes them completely from each other. Essentially, there's no overlap between them. If I have a perfect measurement device and a perfect qubit, it is definitely pointing spin up. My measurement device will never be confused and say that it's spin down. It's just like 2 orthogonal vectors. Just like I can perfectly distinguish something that's moving in the x direction from something that's moving in the y direction, they have no overlap, no component of each other. Okay? They're impossible to confuse. Just like an x vector has no y component, a spin up is in no way spin down. Why are they unit vectors? Well, we'll find out very quickly that the components of the vector correspond to probabilities. And if I measure it, if it is either spin down or spin up, those probabilities have to add up to 1. So whenever we represent a quantum state, it has to be a unit vector because, as we'll see when we start figuring out how the measurement rules actually work, we want those probabilities to add up to 1. And why 2-dimensional? There's 2 possible states. I can have higher dimensional quantum systems, of course, things that have more mutually exclusive states. But for right now, in a lot, but not all of quantum computing implementations, we want to think about 2-dimensional systems because we're dealing with quantum bits. So 2-dimensional, the dimensionality of the vector corresponds to the number of mutually exclusive states. Okay. And now this is just a bit of notation. We're going to denote our qubits as kets. So instead of thinking about like a vector as a V with a little arrow over top of it, we're going to write them down in these fancy bracket notation here. So for example, the 0 state, just so we can talk about them abstractly instead of always having to say, well, an electron that's spin down or a photon that's horizontally polarized, we're just going to call it abstractly the 0 state. If I'm talking about electrons, that corresponds to spin up. If I'm talking about spin down, I'm going to represent it as the 1 ket and represent it as this vector instead. Okay, so the details, how we get to this point, how we get to a bit that we can define as having 2 mutually exclusive states that we control and only consider those 2, that's going to vary a ton between different physical systems. But the end result is always the same. Linear algebra gives us our rule book for quantum mechanics. At the end of the day, one of the goals of especially qubit-based quantum computing and other kinds of quantum technologies is boiling down the system so we can think about it as a bunch of 2-dimensional vectors. There's a lot of details that go into getting that way, but once we have it that way, we can think about it using our simple rules of linear algebra. That's the goal, in a lot of cases. Okay, so far so good? Yeah? Okay, so before we get too abstract, okay, well first off now we have to actually measure something. How do we measure qubits? So what does a measurement do? I have my 2 mutually exclusive states. My measurement is going to tell me which state I'm in. So a measurement distinguishes between 2 or more mutually exclusive states. If I encode my bit in a coin, my measurement is I look at the coin and it tells me if it's heads or tails. If I encode my bit in the polarization of a photon or the spin of an electron, my measurement's probably a little bit more complicated. So once again, two states are mutually exclusive, but being found in one means it's definitely not in the other. The cat example, my measurement is I open the box and take the cat's pulse, see if I get attacked, something that's going to tell me if the cat is alive or dead. Okay? The measurement's going to tell us which of the two states the object was in. So before we get too abstract, let's focus on one particular example. We're going to focus on the polarization of light, because that's something that we can do classical analogies of that we can see very visually. Okay? So what is the outcome of a measurement? So the probability of measuring a system, the rule for measurement is that when I measure a quantum bit, the probability of measuring it in a given state is given by the absolute value squared of the inner product of the output state and the current state of the system. Let's break that down a little bit, but that's kind of our basic rule for understanding how measurements work. Let's say, for example, that I have a quantum system in the zero state. So that means that I describe it as this unit vector. That is the vector describing the state of my system. Okay, now I ask it the question, are you 0 or are you 1? Well, how do I find those probabilities? Well, what I do is I kind of flip that state around. I'm asking it the question, I have the 0 qubit, is it in the state 0? I'm going to take the inner product of my qubit state, which is this 0 state here, the vector corresponding to the measurement I'm making, I've just kind of flipped that around and make that into a row vector, and I look at their inner product, I find that it's 100%. So there's a 100% probability that I find the 0 qubit in the 0 state. What's the probability I find it in the 1 state? I do the same thing. I look at the inner product of those two vectors. That's kind of an x and a y vector. They're orthogonal to each other. They have 0 inner product. The probability is 0%. Okay. Now, nothing fancy going on there. What's the probability that I find 0 to be 0? It's 100%. That hopefully is not surprising. But what makes quantum states and quantum bits a little bit different is that I can have states like this. So what about the plus state, for example, which I can think about as this vector. So instead of being an x vector or a y unit vector, it's a vector that's somewhere up here. Or the minus state, where I put a minus sign between them two and look at a vector pointing up in this direction. They have both a 0 and a 1 component. What does this actually mean? So I can play the same thing. I can say this is my quantum state, and I'm going to ask it the question, are you 0 or are you 1? And to make that measurement, what I do is to find the probability of it being 0, I take the state that I have, inner product of the state that I'm measuring it. So I'm asking the plus state, are you 0? So I'm looking at the inner product of this vector with this vector, and that ends up being when I take the absolute value squared, 0.5, 50%. Inner product is 1 over root 2. Absolute value squared is 50%. So effectively, if I have this state and I ask it the question, are you 0 or 1? Half the time, I'm going to get the answer, I'm 0. Half the time, I'm going to get the answer 1. Okay, so this is just randomness. But what makes this interesting is that I'm not limited to just asking the question, are you 0 or 1? I could ask the question, are you plus or minus? Yeah? So with bits, I'm only limited to, I can ask the question, are you heads or tails, for example. With quantum bits, I can start asking questions like, well, are you this superposition state, or are you this other superposition state? And in this case, I find that the inner product of the plus state with the plus state is 100%. The inner product of the plus state and the minus state is 0%. So if I ask it the question, are you 0 or 1, it's 50-50. But if I ask it the question, are you plus or minus, it's definitely in the plus state. And this is one of the key differences between quantum and classical, is that in quantum mechanics, there's more than one question I can ask. At least that's one way we can think about it. Oh. There we go. Okay, and this is what we mean when we talk about quantum superposition. So these states, the plus and the minus state, they have both a 0 and a 1 component. If we wave our hands and squint our eyes a little bit, we can think about those as being both 0 and 1 at the same time. It's in a superposition of 0 and 1. But when I ask it the question, are you 0 or 1, it's going to be found as one or the other randomly. But the nice thing is I can actually flip this completely around. I can think about my 0 state and my 1 state as being superpositions of plus and minus. And now they are, in a sense, what I was thinking about as my original state 0 and 1, well, they're actually superpositions of plus and minus. They're plus and minus at the same time. When I ask them the question, are they plus minus, they will be found as one or the other randomly. So measurement, this is what we mean when we talk about a measurement basis in quantum mechanics. It's defining what question we're asking, defines which question I ask the particle. And when we think about the concept of a quantum superposition, we always have to remember that it's relative to the basis we're using. Okay, we got a little abstract there. So let's reel it back into something tangible. And we're going to be talking about the polarization of light. To talk about, so this, as mentioned, qubits, we could talk about electron spin, we could talk about polarization of light, we can talk about position of photons, we can talk about the energy states of trapped ions, all these sorts of things. But it's all the same concepts at the end of the day. So let's focus on one that we can see with our eyes. So light carries an oscillating electric field perpendicular direction of travel. The direction of that field is called its polarization. So if we take our polarizers, which everyone got little ones, I made sure to bring myself the big ones. What each of these polarizers do is they absorb light depending on the direction of the field. If I hold my polarizer like this, it lets through all the light that's horizontally polarized, so all the light oscillating in this direction. But if the light is oscillating up and down, I really wish I had a third arm at this point, then we'd find that it would be blocked by the polarizer. Apologies to the online audience for 1 second. I need 2 hands for this. So if I have 2 polarizers, and if I hold them and they're aligned to each other, we see that the light travels through. This one blocks all the horizontal light, this one keeps blocking the horizontal light, so nothing really happens when I add them together. But if I put one in front of the other and rotate it, we see that it blocks all the light. Right? So why do we see that they're blocking all the light in that way? Well, one of them is absorbing all the horizontal light, one of them is absorbing all the vertical light. If I absorb all the horizontal light and all the vertical light, there's no light left. Those are the 2 possible states of polarization. So these are our 2 mutually exclusive states. And how do I make a measurement of my light? Ask whether or not it's horizontal or vertical. I hold my polarizer like this, or I hold my polarizer like this. Okay, so in the wave picture, this might be familiar. This is like kind of like our high school physics. If I have a polarizer, like if I have light polarized at a certain angle, and I take another polarizer, rotate it by an angle theta, the amount of light that comes out is proportional to the input intensity and the cosine squared of the angle between the 2 polarizers. Okay, and we can think about this more linear algebraically by looking at the inner product of the the vector corresponding to our analyzer and the vector corresponding to the polarization of the input light. So we're seeing inner products do come out in how we figure out the amount of energy that comes out. In the quantum picture, though, we know that light is made up of photons. So what happens to a single photon of light at a polarizer? What makes a photon different than the light that we interact with classically in the world around us is that a photon can't be split in half. I have 0 photons, 1 photon, 2 photon, 3 photons. I can't all of a sudden have half a photon. So if I have 1 single photon, then it hits that polarizer. It's not like I'm going to end up with, an 1/8 of that photon or something like that. I either have a photon or I don't. So instead of thinking about it in terms of what percentage of the photon makes it through, I have to think about it in terms of possibilities. Either the photon passes through the analyzer or it is absorbed by the analyzer, one or the other. So we can still adapt Malus's law, we can still adapt our kind of high school understanding of polarization, but instead of thinking about it as the proportion of the intensity that makes it through, it's the probability that the photon makes it through the polarizer. And that's going to be our cosine squared theta. So we have to consider the probability of each event occurring. Okay? So what the polarizer does is it asks the photon a question. It asks the photon the question, are you horizontally or vertically polarized? Is that the only question I can ask with my polarizer? Could ask for the plus or minus. What would the plus or minus look like? Okay, I saw a couple of people do this. Yeah, exactly. Like I'm not limited to asking, are you horizontal or vertical? Because I can do the same trick with the polarizers by holding it at any angle, right? There's no difference. It doesn't care. It doesn't care what horizontal is. It doesn't know about gravity. So I could ask it, are you diagonal or anti-diagonally polarized, or any other combination of angles? So what happens if I ask the wrong question? So let's say that we start off with a diagonally polarized photon. Okay, and I'm going to represent that as a combination of horizontal and vertical. Okay, so how do we break that down? Well, we're going to now say we have a diagonally polarized photon. It hits a vertical polarizer, and there are 2 possibilities that could occur. I could either find the photon to be horizontal, in which case it is absorbed by the polarizer, or I could find it to be vertical, in which case, sorry, these are backwards, in which case it is transmitted through the polarizer. So I can break that down by thinking about that diagonal line on a Cartesian plane, looking at the horizontal component, looking at the vertical component. And intuitively, I can think about this like vector addition, right? How do I make a diagonal line if I only have horizontal and vertical lines? Well, I just stack them up like that, and all of a sudden I've moved diagonally. How do I move in a diagonal line if I only have the access to the moves of a rook on a chessboard? I just do it in 2 moves, and it works out. Okay, so what I need to do is I need to break down my quantum state, which was originally a diagonally polarized photon, in terms of the basis of the measurement. I need to think about it in terms of its horizontal and vertical components. Sorry, that froze a bit there. Okay, and notably, if it does transmit through the polarizer, it is now definitely vertically polarized. Okay, once I've asked it that question, I've what they call collapsed the quantum state. It's now definitely vertical. Okay, so let's go one step further. We saw polarization with Malus's law. When we have 2 crossed polarizers, no light passes through. I'm going to need a volunteer for this one. Anyone want to come up? Yeah? All right, come on up, come on up. Yeah, you. We need 2 people, actually. All right, sorry, what's your name? Suyash? Ah, very nice to meet you.
Yeah, nice to meet you.
So I would like to ask you to hold this polarizer and stare at the people. All right, and what's your name? Mac. Nice to meet you. Can I get you to hold this polarizer? And what I would like you to do is hold your polarizer in front of Suyash such that no one else can see Suyash. Okay? Everyone else should not be able to see Suyash, correct? Okay. So that is because all the light that is going to Suyash, this is only allowing horizontally polarized light through that 0 qubit state. But Mac is holding up this polarizer such that only vertically polarized light will be allowed through, the 1 state. What's the overlap of 0 and 1? 0%, no light makes it through. Now all the light makes it through, but let's keep blocking them out. Let's give them a little private time. So, polarizers, all they do is absorb light. That is all they do. It's not like I insert a polarizer and something starts glowing suddenly or anything. If I insert a polarizer in the middle at this angle, we see nothing changes. If I insert at this angle, we also see nothing changes. But if I start asking questions in different bases, we suddenly see light has made it through the 3rd polarizer, correct? Is that visible to people? Let's rotate slightly so that people on that side can see. All right, we can see a little bit of the light getting through. Thank you very much. So why do we see that? Yeah, good job. So why are we able to see that happen? Okay, so if you weren't able to see it too clearly there, this is the same thing done using polarized light sources. When we insert measurements, we can suddenly see light through systems of polarizers where we weren't able to see it before. If we want to analyze this problem, we need to be thinking about it in terms of which basis we are asking the question in, which is always important to consider when we are working with qubits. Okay, so let's look at the system again. We had we're just flipping it around by 45 degrees. We start off with the diagonally polarized photon. It encounters a vertical polarizer and then encounters an anti-diagonal polarizer. If we get rid of the vertical polarizer, no light should make it through, right? Those are 2 90-degree polarizers to each other. No light gets through. But let's think about it step by step. We have our diagonally polarized photon. It is made up of horizontal and vertical components. And now I ask it the question, are you vertically polarized? Okay, so what I do there is I break it down in the basis that I'm asking the question in. I find that it has a 50% component, well, a 1 over root 2 component that is vertical, a 1 over root 2 component that is horizontal. I then take that inner product, square it, and I find that there is a 50% probability that it makes it through the polarizer. Okay, so it transmits at 50% possibility, but if it does transmit through, we know with absolute certainty that it is now vertically polarized. Okay, we've kind of thrown out the possibility that it was horizontal. It is now definitely collapsed into the vertical polarization state. So now I'm asking a vertically polarized photon the question, are you diagonally polarized? Sorry, anti-diagonally polarized. So how do we analyze that? How do we answer that question? Yeah. Same, yeah. We got to do some projections, and we got to make sure that we do those projections in the basis that we are asking the question in. So instead of projecting onto our Cartesian xy axis, we are going to project onto the plus and minus diagonal axes. We find that once again, there's a 1 over root 2 component of each. So what's the probability it makes it through the anti-diagonal polarizer? It's going to be that component squared, another 50%. Okay, so the photon overall has a 25% chance of making it through. The important thing to note here is that measurement changes the state, and it matters very much so which basis we make that measurement in. Okay, so this is very important for understanding how qubits work in quantum computing. It is essentially all you need to know to understand how qubits work in quantum communication. So Catania is going to be talking a little bit about that tomorrow if you want to learn more about how that works, but that's basically the basics of all you need. All right, so just to refresh, these are kind of our 2 golden rules of quantum mechanics. If we get these, everything else kind of falls out naturally. We can have a particle, a quantum object, a quantum bit that has components in 2 possible states. Colloquially, it's in both states at the same time. But when we measure it, we find it to be in one or the other randomly. However, superposition, this act of being in 2 possible states at once, having a component in each in one of 2 mutually exclusive states, this is always relative to the basis that we are making a measurement in, or equivalently, how we rotate our state before we make that measurement. So a natural question to ask is, how many bases are there? Well, our favorite one, the one that we usually work in, the one that a lot of quantum computational devices are limited to how they measure in, is what we call the computational basis. For polarization, this is traditionally horizontal and vertical. For electron spin, it's traditionally up and down. For ionic energy levels, it's ground state or excited state. All of these are examples of binary quantum systems, and we usually call these states the computational basis. But another basis is the superposition basis, this X basis, where we have the plus and the minus state. It could also involve complex numbers. The phase difference between the 0 and the 1 component could be represented by a complex number, like in the plus I state and the minus I state. All of these are orthogonal states to each other. If I take the inner product of one with the other, we find the inner product is 0. So they are valid bases in which we can make measurements. Generally, for qubits, we can form a basis like this. So there's actually a continuous range of parameters, similar to how we can rotate the polarizer to any angle we choose, but also noting that we can control the phase, the complex relationship between the 2 states as well. So instead of thinking about it as rotations in a circle, we think about it as a point or an axis on a sphere. Okay, so these are kind of our classical bits. Our classical bit can be heads or tails or anywhere in between if we think about it probabilistically. Maybe there's a 50% chance it's heads, a 50% chance it's tails. Whereas our qubit, well, it could be 0 or it could be 1, which we can think about as nodes on a sphere. Or it could be the plus state or the minus state, or it could be the minus I state and the plus I state. And all of these are potential possibilities. So it's kind of like in this classical state, if I look right in the middle, that's 50% 0, 50% 1. 50% of the time it's going to be heads, 50% of the time it's going to be tails. If I look anywhere on the equator of this sphere, that includes the plus state, the minus state, the plus I state, the minus I state. Those are also 50-50, 0 or 1, heads or tails. But I can make measurements that distinguish between them as well. So it's like it balloons out that line into a sphere. Okay? Now, where it gets interesting for computing purposes is when I start scaling this up. So if I have a series of bits, these zeros and ones, well, there's a whole bunch of probabilities. I can assume that they can be arbitrarily correlated with each other as well. And there's going to be 2 to the n possible states of the system. Right? So it could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. As I add more bits, I get, double the number of possibilities effectively. And if I assume there can be arbitrary correlations, there's 2 to the power n numbers I need to describe that. For quantum bits, I don't have to just worry about the correlations between 0 and 1, but also between plus and minus, plus I, minus I. Same argument that Steph was making earlier about it ballooning into the outsides of that density matrix, kind of filling up that square. This sort of fills up a higher dimensional space that we can access that ends up taking 2 to the n times 2 to the n numbers to describe if I want to understand both the probabilities of zeros, probabilities of ones, as well as what happens when I make any arbitrary measurement. So there's an exponential separation. Now, if I want to design algorithms, as Nathan will be talking about in the next session, It's not as simple as every quantum algorithm gets an exponential advantage, but that is the potential there for certain algorithms if we can control our qubit state evolution and our measurements properly. That's also why you don't get more than exponential, because that's the amount it takes to just simulate the qubits with classical bits. Okay, so in the few minutes I have left, how can we actually build these qubits? So that's, if I want to start building qubits into a usable system, I need to consider the DiVincenzo Criteria. These are kind of like 5 simple rules for building a quantum computer. If I can satisfy these rules, there is hope that I can use my system to build quantum computing devices and other sorts of quantum information processing devices. Okay, so proposed by David DiVincenzo in around 2000, kind of at the start of the quantum computing boom that started with, depending on how you want to talk about it, either with Richard Feynman or with Peter Shor. Okay, so first thing we need is a scalable system with well-characterized qubits. So I need something where, it's one thing if I have a qubit, like a single polarized photon, but I need something where I can keep introducing more and more qubits, and it doesn't get like exponentially harder to do so as I introduce more qubits. Okay, this is not necessarily easy. I need the ability to initialize the qubits to what they call a fiducial quantum state. So one of the ones we like to think about a lot is just initializing them all to the state 0, making all my photons polarized horizontally. Okay, so I need to be able to do some operation, all my qubits go to the 0 state, the ground state, the horizontal polarization state, whatever I have there. I need decoherence times longer than the gate time. So I'm going to do some operations. I'm going to flip my qubits to different quantum states and different superpositions. And what's going to happen is those qubits are going to couple to the world around them. They do not exist in a closed system. There is stuff happening around them all the time. I just need the time scale by which they talk to the world around them to be much longer than the time scale by which I'm doing my operations and my measurements. Okay? I need a universal set of quantum gates. I need to be able to not just be able to flip between zeros and ones, I need to be able to access those superpositions, and I need to be able to entangle those qubits together. It's not just enough to have one qubit, I need to have entangled sets of qubits, or else I'm basically doing something that scales easily for a classical computer to simulate. So an example set that you'll probably hear a lot about as a universal set of quantum gates is something called the Hadamard gate. This gate, what it does is it flips 0 to the plus state and 1 to the minus state. It essentially allows us to create superpositions. There's the T gate, which looks something like 1, 0, and then, so in matrix form, if matrices are familiar to you, this implements a phase between the 0 and the 1 component. If they're not, all it's basically doing is kind of shifting the relative complex phase between the 0 and the 1 component by pi over 4. So something that controls the phase between the two, kind of where it sits on that circle in this direction. And we need something like the C0 gate. What this does is it lets the qubits talk to each other, correlates them to each other, effectively entangles one qubit with another qubit. If we have these 3 gates, we can build any circuit we want, if we're patient enough. So for example, I can build a swap gate out of 3 C0 gates. I can build a controlled phase gate out of a C0 and 2 Hadamards. But we can see it gets a little messy. This is the Toffoli gate, the controlled not, and I can do it with that simple set of gates, but it looks a little something like this, which is honestly not terrible, but still getting to be a little bit of a mess. For arbitrary gates, it gets to be even more of a mess. But generally speaking, it might not be easy, but any gate can be faithfully approximated using that universal set of gates. And finally, I need a qubit-specific measurement capability. If I have my long string of qubits, I need to be able to turn on my laser, turn on my measurement, and say, okay, I'm looking at qubit 3. Qubit 3, I'm going to measure you, but I don't want to measure everything else around it. Okay, so I am running a little bit out of time, so I will skip that particular part, but let's look at the photon system, for example. So we need a scalable system with well-characterized qubits. I can produce photonic qubits, individual photons of light, using, for example, a quantum dot emitter, which is basically a artificial atom system where I blast it with light, put it to an excited energy state, let it decay and get exactly 1 photon out. Or I can do it using nonlinear optics instead. I need the ability to initialize the qubits to a fiducial state. So for example, I could do something like have them all go through a polarizer at the start. Usually with the systems I'm actually making my photons out of, they come out with a well understood polarization state, so that's already done. For other systems, some of the cluster state examples, some of the things that Steph mentioned a little bit, that Xanadu and other companies like that do, we actually start with a different initial state that has them all entangled at once at the very start, which is possible to do using these systems as well. I need decoherence times longer than the gate times. For those entangled versions, for the continuous variable stuff, that's one of the big challenges for photonic quantum computing. But if I'm using it for quantum communication, or if I'm using it starting from those photons, well, the challenge is going to be producing them, but once I have them, this is a image of the cosmic microwave background showing that it remains polarized, so polarization does not necessarily decohere, it does not interact with the environment. We lose the photons all the time, that's a problem, but losing the quantum state is not too much of a problem. Erasure is a big problem though. We need a universal set of quantum gates. This can be done. Making photons talk to each other is the big challenge there. That starting with that entangled cluster gets around a little bit. And finally, we need a qubit-specific measurement capability, which is usually coupling a photon into an optical fiber after a polarizer and measuring whether or not it makes a photon detector go click. So using photons as an example, it does satisfy all 5 of these criteria, but only if we look at it in just the right way, and noting that no matter if we try to fix something to satisfy one of them, we're going to make our life a lot harder on one of the other ones, generally. Okay. Of course, these are not the only ways to make qubits. We can make qubits out of photons, where we create a photon and code information in its polarization or its color. We can use atoms and ions, isolate a single or small number of atoms, use their electronic energy as a qubit. I can look at spin, so a lot of the very early tests of quantum computing were done using the spin state in a collection of atoms in NMR experiments. So basically, if I think about like a molecule made up of many atoms, each with their own nuclei, I use the spin of each nuclei as a qubit, whether or not it is spin up or spin down. As well as superconducting circuits, where we're actually kind of designing our qubits in fabrication facilities, cooling them down to below 1 Kelvin, and using their electronic properties, looking for coherences there. So in each of these, there's like companies working on all of these, as well as, of course, researchers at U of T, where I'm from at UWaterloo, and all around the world working on these platforms. And with that, hopefully, that dispelled a little bit, but thank you so much for coming once again, and yeah, thanks for having me.
One, two, three. Okay. All right. So thank you very much, Dr. John Donohue from University of Waterloo. So at this point, we're going into Q&A. For the in-person audience, if you have a question, you can raise your hand, and I'll be walking towards you with the mic. And online audience can also put their questions in the chat. One question over there.
Hello. This might seem like silly or something, but you had like a general form of a state, and then you had like the phase doing it at the one. Yeah. Does it matter? Do you know what I mean? Like, is it just convention, or like, does it, like, you know what I mean? Like, yeah. Could you put the phase on the zero, like the zero state, like the dephasing?
No, that's a good question. That's a good question. So when I showed the general form of a qubit, it was something like cosine theta 0 plus sine theta e to the I phi 1, something like that. I put the phase on the 1 term because all that matters is the relative phase between 0 and 1. Whenever we make a measurement, we saw that there was that absolute value sign around everything. So if I gave both a phase, like ultimately what I'm going to measure is something that's proportional to like phi 1 minus phi 2. So I can just kind of group everything onto the 1 term and ignore the phase on the 0 term, as long as I note what the relative phase is between the two. Yeah, and that's purely convention. I could have easily put the phase in the 0 term and it would have all worked out the same. Yep. Oh, I think I see one over there.
Okay, so you might have heard of something called a unitary matrix,
yeah,
or unitary operator.
Absolutely.
So I heard like unitary matrices has to do with quantum computations. So how is the thing of being unitary so intimately related to quantum linear algebra?
Yeah, so a unitary matrix is a matrix that satisfies certain properties. Effectively, the unitary times its conjugate transpose is the identity matrix. What's important about unitary matrices in the context of quantum computing is similar to the reason why we had to restrict ourselves to unit vectors. We need all the probabilities to add up to 1. It doesn't make sense if we have a qubit where there's a 50% probability we measure it to be 0 and 125% chance we measure it to be 1. So unitary matrices have the nice property where if I apply a unitary matrix to a unit vector, it's going to remain a unit vector. It's going to maintain those probabilities. So that's kind of like the 0th order reason why unitary matrices are important. They keep probabilities maintained. Well, sorry, they don't maintain probabilities, but they maintain conservation of probability.
Okay, but how do you even visualize a unitary matrix?
Yeah, so any unitary matrix, if I think about that sphere representation that we kind of glossed over a little bit for a qubit, it's going to be a rotation in that sphere. So if I have, say I have something at the north pole of that sphere, there's going to be a unitary matrix that rotates me to the south pole, and a unitary matrix that takes me to the plus state or the plus I state. These are all going to be represented ultimately by unitary matrices. Yeah. And in fact, like, that's also general enough. Any unitary matrix will rotate me, and I can make any rotation out of some unitary matrix. Yeah, sure.
You had these operators,
Yeah.
and you said these are kind of like they're the building blocks of all the operations you want to make in quantum computing, right?
Yeah.
You said that. Like, how do you know that? Like what is there? Is it like, how do you know those are? Yeah.
So I actually, that's actually probably a great question for the next speaker, is what the proof is for there being, for HT and C naught being a universal set.
Sorry, I didn't mean to cut you off. Because in quantum computing, you want to do more operations than you would in classical.
Yeah.
So it's like, how do you even define what are all the operations you want to do, or is that?
Oh yeah, sorry, yeah, no. So the important thing there with the universal set is that if I can make a device that can faithfully implement those 3 operations, then I can build any other operation out of combinations of those operations. So you might have heard about universal gates in the context of classical computing, where if I want to build any arbitrary classical circuit, I can do that using just a NAND gate. That doesn't mean that the NAND is the only operation I want to do. It's just that if I want to make an OR gate, I can do it using a few NAND gates. If I want to make a proper AND gate, I can do that using a few other AND gates. If I want to make an adder, I can take all the different components of it and make them out of NAND gates, and effectively I'm done. So that might not be the best set of gates for whatever your implementation of quantum computing is. There might be another universal set you want to use. But if you build something that has access to those 3 gates or an equivalent set of 3 universal gates, then I can do anything else with it. If I have access to other gates that are easy to use in addition to those 3 that I can, press a button and do more easily as opposed to building them up with those blocks, that might help me. But in principle, that's enough. If I have patience and long decoherence times and all that jazz.
We actually have a question here from Zoom as well.
Sure.
Considering the different types of qubits that are out there, if you were to store information for a qubit in terms of as a photonic qubit, what are the advantages compared to the other qubit, or if there are any differences in terms of storing information?
Yeah, so storing information in a photonic qubit, there's only one reason you'd ever want to do that, and that is for quantum communication. Because photons travel at the speed of light, they don't interact very much with their environment, especially in vacuum or near vacuum. I can encode a quantum bit into a photon, send it somewhere else, whether that's as a node in other quantum computing systems. So if I want two superconducting qubits talk to each other, they need to exchange a microwave photon effectively. If I want to build a quantum communication system, I'm usually using infrared or visible photons. But if I want to use a quantum memory, I probably don't want to use a photon because it travels at the speed of light and I can't really stop it. So for memories, the spin systems generally have exceptional coherence times. So they're often thought about like spin-photon interfaces as a great way to kind of get the advantages of some of the both. But yeah, so I'm going to want something with a much longer decoherence time, importantly relative to its gate time. So I can have something that maybe holds quantum information for many microseconds, but if my gate also takes a microsecond, that's a problem. If my gate takes a nanosecond, that's great.
So in the classical, like when you talk about bits, so in classical you can have like, two outcomes, possibly 0 and 1.
Yeah.
And then like we talked about in quantum where you can make superpositions, and like that provides you with more and more states that one bit can have.
Yeah.
So then it's like, yeah, sure, you're storing more information with one bit, but then to measure that information, you're gonna need even more like sensors or like measurement devices that will have to measure, because like for each different basis, you'll probably need a different measurement sensor or device, right? So then isn't that become like unpractical? Because then if you have like, let's say if a bit can store 4 pieces of information, then you'll probably need 2 measurement devices, because like for the basis to say whether it's this or whether it's this or this, right?
Not quite. So you're right that we'll need to have like the proper gates in order to transform whatever basis we're measuring into the computational basis to measure it. Oftentimes, a lot of the systems that we work with, the ionic systems, superconducting systems, they can only measure if it's 0 or 1. That's all they can do. What they can do is they can have operations that kind of switch between those bases in order to measure in those other bases. With the polarization, that's a bit of a special case where we actually can control exactly which basis we measure in. Yeah, and there's an important distinction between like what you're kind of hinting at a bit almost sounds a bit like analog computing, where instead of thinking about it as a bit that's 0 or 1, I think about it like the level of water in a flask, where it can be anywhere from like full to empty and all the way in between. There are still only 2 mutually exclusive states for a qubit. It is either 0 or 1, but it could also be either plus or minus. Plus and 0 are not mutually exclusive to each other, although like, being 50% full and being 40% full, despite being very close to each other, are mutually exclusive. So that's one of the big differences there. I don't want to delay Nathan too much, but I did see one more question up here. Yeah. Yeah, does that answer it, kind of? Yeah, okay.
Question. So, I see that the math you showed corresponds a lot to like how you visually describe the light. Would you say it's more of an analogy, or is it actually what's happening? Like, how like with spin you say like it's an analogy that it's spinning, it's not really spinning. So is it like with the light, what you described it, is it an analogy, or is it like actually what's happening?
This is why I love polarization, because that's actually what's happening. The difference between if I wanted to use polarization for quantum computing or quantum communication versus what we can do with the big polarizers is that I need to think about it as one individual photon. And with light, we're talking about a whack ton of photons, something like 1,000,000 trillion photons. But the effects that we're seeing are an exact thing. It's light. Photons actually do have an electromagnetic field, just as visible light, classical light around us actually does have an electromagnetic field. So the analogy is a little cleaner than spin. Yeah. Okay, I think, maybe let's make that the last question, I think. Yeah. If you want to set up, you can.
Hi, thank you for the presentation. I'll keep this short.
Of course.
On one of the slides, you had the possible number of states between the classical and a quantum computer system.
Yeah.
Which was 2 to the n and 2 to the n times 2 to the n.
Yep.
What's the 2 additional pieces of information you require for each qubit that was not in the classical bit?
Yeah, it effectively comes down to the phase. So what we're looking at is the coherence there. So we can have correlation between a bunch of classical bits. So the number of possible states still grows as 2 to the power n. And if I make those correlations arbitrary, then it's kind of like 2 to the n numbers that I need to know to figure out exactly what describes my classical state. And that, in a sense, corresponds to well, actually not in a sense. Legitimately, if I think about this as a matrix, that's the diagonal elements along a matrix. There's going to be 2 to the n elements there. But if I have a quantum state, and if I have entanglement, if I have coherence there, and if I have phase information in there, that's going to fill up the remainder of the matrix, and that's going to be where I get that second 2 to the power n in there. Yeah, I don't have a board on here, but I can sketch that out during the free time if you want as well. maybe a
Thank
bit
you.
more of a concrete way. All right, and with that, thank you all so much. How's it going?
Very well. Thank you very much, Dr. John Donohue, for the very informative talk. We have some questions in the audience from the Zoom, but unfortunately, due to the restriction from time, we'll not be able to take them right now.